This is SpaceTime, Series 28, Episode 37, for broadcast on the 26th of March 2025. Coming up on SpaceTime, a new exoplanet discovery using a new system, a new study claims dark energy could be evolving over cosmic timescales, and claims the moon's magnetic field is more dynamic and lasted far longer than previously thought. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered a potential new exoplanet. The new planetary candidate, catalogued as TOI 2818c, is estimated to be between 10 and 16 times the size of the Earth, but with an orbital period less than 16 Earth days. It was found just over 1,000 light-years away in a planetary system in the constellation Papus. A report in the Astrophysical Journal claims the new discovery was made using transit timing variations. These involved using the timing of a known planet transiting across the host star to infer the presence of a second exoplanet in the system. After identifying an unusual trend in the movement of the hot Jupiter planet TOI 2818b, the authors ran a series of model simulations. They pointed to the presence of a small planetary companion. The study's lead author Ben Monte from the University of New South Wales says it's rare for hot Jupiters to have other planets near them. So this new planet could have serious implications for how hot Jupiters form, and in turn it could help astronomers understand other systems. An exoplanet is any planet outside our solar system. Like the planets in our solar system which orbit the Sun, most exoplanets orbit a host star. So far, over 5,500 exoplanets have been confirmed by NASA. But there are trillions more expected to be out there waiting to be discovered, and that's just in our Milky Way galaxy. Of the known exoplanets, around 500 are known to be hot Jupiters. These are hot gaseous worlds like Jupiter, but orbiting extremely close to their host stars. Usually, each orbit takes just a few hours or a couple of days at most. Even lesser known are companion planets to the hot Jupiters, planets orbiting the same star as the hot Jupiter. One way of hunting exoplanets is known as the transit method. It involves monitoring planets as they pass in front of a star as seen from Earth. When this happens, the planet briefly blocks out some of the star's light. That dip in stellar light, the regularity of the dip and its duration, can tell astronomers a lot about the planet's orbit and size. And if it's close enough for a spectra to be taken, scientists can also find out about the planet's atmosphere, possibly even its composition. Monte says planets usually make good clocks, and an exoplanet's orbit around a star should remain reasonably stable, ensuring consistent timing between transits. However, if you have more than one planet at play in the system, then the planets will tend to push each other around with their gravity, and that will make each of the planets speed up and slow down just a little bit. This means the transits will arrive slightly earlier or slightly later than normal, and you can then use that to infer another planet is causing these timing variations. Monte and colleagues made their discovery by going through 3 years of data from the NASA Transiting Exoplanet Survey satellite tests. One known exoplanet is TOI 2818b. It was discovered using the transit method. However, when analysing the data, the authors noticed that its transit dips were not evenly spaced. They were occurring closer together over time. Something must have been influencing this planet's orbit, and that prompted a closer investigation. The tricky thing is there are a number of plausible explanations as to why a planet should arrive early. For example, tides of the star itself can impact the gravitational pull on a planet, exactly the same as what we see between the Moon and the Earth. But when this is the case, the planet is typically spiralling inwards, about to get swallowed by the star. That would make the transits of this planet arrive earlier and earlier. So, Monte and colleagues needed to work through all the possible variations of explanations that could cause the timing variations seen in the data. After extensive examination, the only option that fitted all the observations was the existence of another planet in the system. The first exoplanets were discovered back in the mid-1990s. While scientists haven't yet found an exoplanet that can support life like the Earth, they have identified a number of Earth-sized rocky exoplanets, some of which are in the habitable zones of their host stars. That's the region around a star where temperatures would allow liquid water, essential for life as we know it, to exist on a planet's surface. Monte says whenever astronomers find new planets, they throw up new puzzles about how these planets are formed, and hot Jupiters are a great example of that. Hot Jupiters were the first exoplanets discovered, but scientists really don't fully understand exactly how they form or even why they're there.
We know that when stars have planets, and when these planets are transiting, so they pass along our line of sight, blocking the star, these planets make excellent clocks. They orbit their stars perfectly Keplerian motion. Every time they come back around, they block the star in the same way for the same amount of time. And so when that doesn't happen, if these transits are occurring early or late, we know something else is going on. There's something else in the system that's causing some sort of dynamics to occur, and that's affecting the planet that we see. And so that's exactly what happened here. This is one star that we knew had a planet already, a hot Jupiter. So every 4 days, this giant planet went around the star, blocked the lights. But in our team, working with a PhD student here, Brendan McKee, we found that this hot Jupiter was arriving earlier and earlier and earlier. So it looked like it was almost spiraling into its host star, which led us to think something else is going on here, to look at the system more closely. And ultimately, we were able to determine that the thing that's going on is that there's another planet in the system.
Now, this is not unusual. A lot of exoplanets that we find have siblings orbiting the host star, but we don't see that very often with hot Jupiters.
Yeah, that's right. So we know that most planets are in multiple systems, like the solar system, right? There's 8 planets here. And about 10% of all of the planet systems that we see have these timing variations. So we see the interactions between 2 planets. These are typically planets near what we call a resonance, and so they orbit each other in some ratio of periods. So say 10 days and 20 days or something like that. So you get the same effect of pushing a child on a swing, that every time the 2 planets come to each other at the same point in the orbit, they give each other a little kick, and so these little kicks add up, and all of a sudden you get a big perturbation. What is rare is to see this in a hot Jupiter system. There's only about 5 or so hot Jupiters that have any sort of companion that has been detected, meaning another planet. And so this is a fairly small sample that we've added to, and these are important because they help us understand how these hot Jupiters form.
We're talking about something near the hot Jupiter, not something much further out, I take it.
That's right. So we weren't able to uniquely say exactly where the other planet is. There's a solution at 8 days. So the hot Jupiter goes around every 4 days. This other planet could be at 8 days or 12 days, or inside of the hot Jupiter even at 2 days. And there's a solution that works with all of these. We need more data to figure out in which of these orbits it is. But we know that, in a resonance with the hot Jupiter, there's a planet that's probably between about 5 and 10 Earth masses, and that's all you need to create these perturbations. So it's a small thing. It could have even started perhaps as a moon of this hot Jupiter and got pulled away by the tidal forces from the host star over time. It's possible. We don't really know where it's formed from.
There are a lot of questions which are being raised as a result of this, such as the sort of dynamical forces that could be involved. And you looked at 2, hot excitations and another one called cold migration.
Yeah, that's right. So there's 2 main theories for how hot Jupiters form. We think that in almost all cases, they would have formed much further away from their star, like where Jupiter is in our solar system. There's just not enough material close to a star early in its life to create a Jupiter. So it forms further away and it moves in. And there's 2 different ways that could happen. One is that it moves very smoothly through the protoplanetary disk when the system is young and just migrates in a very calm way. We call this cold migration. And the second one is warm or hot migration, where there's some sort of interaction, say 2 giant planets nearly collide with each other, kicks one into a big orbit that eventually spirals inwards towards its star. And so that's a much more dynamic process, probably perturbs everything else in the disk. We would expect if that was common, then these planets typically wouldn't have other planets in the system. They would all get ejected through this exciting process, where cold migration would preserve planets along the way. They just kind of smoothly migrate in with the hot Jupiter. And so the more hot Jupiters we can find with companions or rule out companions with, that can help us understand how common these 2 different methods are. We don't think it's strictly one or strictly the other. We think both happen at different amounts of time. It's just a matter of then trying to figure out how common each one is. And so this and other planets like this will help us really understand how common cold migration is.
That doesn't just work for distant exoplanets. We can employ that same technique to try and find out more about our own solar system. Because if you look at the NEIS model, we think that's how our Jupiter and behind it Saturn acted in the early days of the solar system. They moved inwards a little bit and then migrated back outwards again.
Yeah, absolutely. This isn't a theory that was developed recently. This is a theory that goes back to our own solar system. And a lot of what we think we understand about planet formation comes from our solar system. The NEIS model and then the Grand TAC model, which kind of builds on the NEIS model, both predict that Jupiter and Saturn and all the planets would have moved around quite a bit in the early solar system because of interactions with the protoplanetary disk when the system was young. We're talking the first 10, 20, 30 million years of the solar system's life. And so that is certainly something that the exosolar systems resemble in many ways.
And as Jupiter moved inwards, it did two things. One, it flung a lot of material into the outer part of the solar system, but at the same time, it also caused the compression of protoplanetary material that was already in front of it, that is towards the sun, and that helped form Mercury, Venus, Mars, and the Earth.
Yeah, what we really need for planets to form is a change in density. If you have everything just in a disk and it's all uniform, you don't really get the interactions that you need for stuff to clump together to start forming a planet. You need stuff to move past each other, and then different material gets caught, either just through electrostatic forces or through gravity, and then you start building little clumps that get bigger and bigger in time. And so anything you can do to speed up that process helps. The protoplanetary disk only lasts a few million years, so you need to form your planets quickly. And so if you can have giant planets moving around, causing clumps, causing overdense regions, causing material to just shift its orbit a little bit to bump into new stuff, that really helps you form planets more quickly and more effectively before your protoplanetary disk dissipates.
So where to now with this research?
So there's still a lot of planets to be characterized with TESS. TESS has now been observing for just over 5 years. So the baseline, how long we have data for, is longer than the Kepler mission. So we can start looking at systems and seeing more subtle dynamical effects that you couldn't see with Kepler because the timescale wasn't long enough. The mission only went for 4 years. We can now start seeing in TESS. It also is all sky. So where Kepler was only one field of view, TESS is reobserving across the whole sky. And so there's a lot of data, a lot of hot Jupiters that haven't even been discovered yet in TESS because there's just so much data to sift through that not only will we be able to find thousands of these things, they're big signals, giant planets close to their stars, but we're going to have this many-year baseline to start looking at the dynamics of these. So it's a really exciting time to be working on this because the data is just so rich and every month becomes richer. So that's one aspect that we're excited about. We're also going on into the dynamics of planets around binary stars. So in the same way that we can have perturbations when a planet interacts with another planet, if there's two stars, like canonically Tatooine from Star Wars, if you have two stars with a planet going around it, you'll see interactions between those three objects together. And so we can measure the two eclipses very well over lots of different telescopes, lots of different data sets going back decades, combining those together to look for really subtle signals that are the sign of a planet. And so our next big project is trying to find circumbinary planets around binary stars.
That's Senior Lecturer Ben Monte from the University of New South Wales. And this is Space Time. Still to come, a new study claims dark energy could be evolving over cosmic time, and there are claims the moon's magnetic field has lasted far longer than expected. All that and more still to come on Space Time. A new study suggests that the mysterious force known as dark energy may be evolving, changing how it will affect the ultimate fate of our universe. The findings come from the Dark Energy Spectroscopic Instrument DESI, a survey putting together the largest three-dimensional map of the universe ever made. It's designed to track dark energy's influence over the past 11 billion years. The new observations, reported on the pre-press physics website archive.org, are showing hints that dark energy, widely thought to be a cosmological constant, might actually be evolving over time and in unexpected ways. DESI is an international experiment with more than 900 scientists from over 70 institutions around the world, and it's managed by the United States Department of Energy's Lawrence Berkeley National Laboratory. DESI scientist Alexei Lathund-Harnett from the University of California, Santa Cruz, says the findings are extremely intriguing. They suggest that science is on the cusp of a major discovery about dark energy and the fundamental nature of the universe. Taken alone, DESI's data are consistent with the standard model of the universe, the so-called lambda cold dark matter theory. However, when paired with other measurements, there are mounting indications that the impact of dark energy may be weakening over time and that other models may actually be a better fit. Now, those other measurements include the light left over from the dawn of the universe, known as the cosmic microwave background radiation, or CMB. Others include exploding stars known as supernovae and how light from distant galaxies warp by gravity, known as weak lensing. The findings suggest astronomers need to modify their standard model of cosmology in order to make these different datasets make sense together. So far, the preference for evolving dark energy hasn't risen to 5 sigma. That's the gold standard in physics that represents the threshold of a new discovery. However, different combinations of the DESI data with the cosmic microwave background, weak lensing and supernovae datasets range from 2.8 to 4.2 sigma. And anything above a 3 sigma event has a 0.3% chance of being a statistical fluke. Nevertheless, many 3 sigma events do fade away as more data becomes available. DESI is one of the most extensive surveys of the cosmos ever conducted. The state-of-the-art instrument, which captured light from 5,000 galaxies simultaneously, is now in its 4th of 5 years of surveying the skies. And there are plans to measure approximately 50 million galaxies and quasars by the time the project ends. The new analysis uses data from the first 3 years of observations and includes nearly 15 million of the best measured galaxies and quasars. It's a major leap forward, improving the experiment's precision with a dataset that more than doubles what was used in DESI's first analysis, which also hinted at an evolving dark energy. And it's not just that the data continues to show a preference for evolving dark energy, but that the evidence is becoming stronger and stronger now than what it was before. DESI tracks dark energy's influence by studying how matter is spread across the universe. See, events in the very early universe left subtle patterns in how the matter is distributed through space. It's a feature which scientists refer to as baryonic acoustic oscillations. That pattern is providing a cosmic scale standard ruler, with its size at different times directly affecting how the universe is expanding. By measuring the ruler at different distances, it shows scientists the strength of dark energy through history. As the data is getting more and more precise, astronomers are finding potential cracks in the model, and they're realizing they may need something new in order to explain all the results when they're put together. It's a fascinating puzzle, and needless to say, we'll keep you informed with what they find. This is SpaceTime. Still to come, claims the moon's magnetic field lasted longer than expected, and later in the science report, a new study warns that sugary beverages may be increasing a woman's risk of mouth cancer. All that and more still to come on SpaceTime. New data released by Beijing from its Chang'e 6 sample return mission to the far side of the moon has shown evidence of what appears to have been a significant resurgence of the moon's magnetic field about 2.8 billion years ago. The findings are offering new insights into the dynamic history of the lunar magnetic field and consequently its impact on the moon's interior and surface evolution. China's Chang'e 6 mission was launched back on May the 3rd last year from the Wenchang Satellite Launch Center on Hainan Island. Its lander and rover touched down on the lunar far side on June the 1st. The lander's robotic scoop and drill then took samples of the lunar regolith total mass of 1,935.3 grams. These were placed into an ascent module, which was then launched back into lunar orbit, where it rendezvoused with the orbiter module and was transferred to an atmospheric re-entry module for the return to Earth. The samples have provided the first basaltic rocks and regolith from the moon's far side, in the process filling a crucial gap in science's understanding of the lunar magnetic field's history. See, previous studies based on samples from the lunar near side were able to put together a general timeline of the moon's magnetic field, but they left out key uncertainties about its evolution. The new research has undertaken paleomagnetic analysis of the samples, measuring the ancient magnetic field strengths ranging from 5 to 21 microteslas. The findings show a resurgence in magnetic field intensity at 2.8 billion years. That follows a decline around 3.1 billion years ago. The findings challenge the previous hypothesis that the lunar dynamo weakened after 3 billion years and the lunar core solidified and has remained inactive ever since. The authors believe the magnetic revival could have been driven by a basaltic magma ocean or possibly precessional forces with potential contributions from core crystallization. Now, it all suggests that the moon's interior has remained geologically active for far longer than originally thought, and that suggests significant fluctuations in the lunar magnetic field between 3.5 and 2.8 billion years ago, all as a result of a highly unstable dynamo during this period. It's a fascinating discovery and changes our understanding of the moon's history. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has found that consuming lots of sugary beverages may increase a woman's risk of mouth cancer, regardless of whether or not they smoke. The findings, reported in the Journal of the American Medical Association, looked at data on 162,602 women, 124 of whom developed mouth cancer over 30 years of follow-up studies. Overall, women who drank one or more sugary beverages per day were 4.87 times more likely to develop mouth cancer than those who consumed less than one sugary drink a month. Now that's equivalent to an extra 3 cases of mouth cancer for every 100,000 people. When heavy smokers were excluded, the increased risk from sugary drinks was even higher, with women who drank one or more drinks per day at 5.46 times the risk of mouth cancer compared to women who drank less than one drink per month. The authors say the findings may reveal a previously unknown cause of mouth cancer in women, and so further studies should look to see if the same thing is true among men. A new study claims agricultural drought is likely to become harder to predict as the world continues to heat up. The findings, reported in the journal Nature Climate Change, is based on statistics and computer simulations showing that predictability of droughts may decrease by more than 70% if the world warms to either 2 degrees or 3 degrees Celsius above pre-industrial levels. It shows Australia is one of the most affected regions in the world, along with North America, Amazonia, Europe, and both Eastern and Southern Asia. The authors say this decrease in predictability is due to changes in the soil, as well as the interactions between the land and the air, and increasingly dry conditions more generally. A new study warns that less than half the claims made about ADHD symptoms in popular TikTok videos align with current scientific and clinical standards. The findings, reported in the journal PLOS ONE, assess the content of more than 100 of the most popular TikTok videos with the hashtag ADHD. They found that less than half of the video's claims about ADHD were accurate. They then asked 843 undergraduate students about their TikTok ADHD viewing habits and what videos they would recommend. Students either formally or self-diagnosed with ADHD reported watching hashtag ADHD TikToks more frequently than students who didn't have ADHD. And those who watched those videos were more likely to say they would recommend them regardless of how accurate they really were. While the authors acknowledge social media can provide useful information and a sense of community for those with ADHD, they often don't match expert opinion and could lead to people overestimating ADHD prevalence and think more negatively about their own symptoms. LG and Samsung have just released their latest high-tech TVs. With the details, we're joined by technology editor Alex Zaharov-Reutt from techadvice.life.
I just saw LG's 2025 range. They go from smaller TVs that also work beautifully as monitors, 32-inch, all the way through to 100-inch TVs. I mean, there was an 80-inch transparent LED, all that stuff we see in science fiction. But one of the TVs that LG has been working on for some years, as well as their market-leading OLED, where each pixel is its own light source and you can have ultimate blacks because everything is switched off. There's no light shining through a liquid crystal display that then has to show black and then also have light going through it. QNET is quantum dot and nanocell technologies, and these use mini LED backlighting to create a vibrant picture. Now, there are different levels of this QNET technology. LG uses a branding called EVO to denote the higher quality versions of its technologies. And when I saw a QLED and then a QLED EVO side by side, well, you can see that the EVO version had even more rich colors. It was able to display even more colors than the cheaper version. But this is all in the aim of giving consumers a modern television with all the streaming and all the apps that you expect. Now, one of the things that LG is doing is they're offering 5 years of updates for the television operating system. This is important because just like when you buy a phone, it has all sorts of security and feature updates, and you get the next version of iOS or the next version of Android, and you've got new features, and also, as we were saying before, importantly, security updates. So this is important for TVs because if your TV's stuck, you had it for 5 years and you can't update it anymore, there may be vulnerabilities. I mean, there's a reason why they don't have the little cameras on televisions anymore. Now, they have microphones now, again, because you can now talk to your TVs and get it to change channels or change brightness or improve the vocal track so the voices are louder. But if your TV is several years old, it can have vulnerabilities. Now, Samsung has also come out with its new range of OLED TVs, and Samsung is the other company that's making OLEDs. And these TVs come with 7 years of security and OS updates.
It's really sad, Bud, isn't it? In the olden days, in the days of cathode ray tubes, you'd buy a TV, it'd last you 20 years or so, and you'd only upgrade when colour TV came out or when we moved to flat screens.
Well, in a way, it's the same, because flat screens from 10 years ago, a lot of them wouldn't necessarily have had internet connections, or you would have had to have plugged in an Ethernet cable or Wi-Fi, and that can be turned off. So the TV, the flat screen TV, is still a flat screen TV. It'll still pick up free-to-air channels. It might have some measure of internet connectivity, but if that is turned off, the TV cannot be hacked into.
So it still can do what it can do, but it just misses out on the newer features.
It does, and the benefit of being able to plug an Amazon Fire Stick or a Google Stream Box or an Apple TV is that is then on HDMI 1 or whichever HDMI you've got. And this could also be like for a Foxtel box as well. And you are using that as the TV operating system because it's plugged into an HDMI source. So you're sort of bypassing any of the smarts in the TV at all, and you're offloading it all to whatever's plugged into the HDMI port. And that device is connected to the internet, and that device is getting updates.
That's Alex Zaharov-Reutt from TechAdvice.life. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.